I'll take it away. So, hey, my name is Ghassan. I'm the head of technology. And also, yeah, if you have any questions about the society, leave them to the end to Matt or text them to him. But if you have any questions at any point on the workshop itself, you should like forward them to me directly in the Zoom chat, and I'll read them out and try to try to solve them as we go. So first of all, we sent a link for GitHub repo, which has the beginner workshops, and we will be using Google Colab, which is an environment provided by Google, where you can run notebooks. So we just simply go to Google Colab from GitHub, and we're in the first notebook. So basically, the way that these sessions are going to run is that there's some like prior reading before the session itself, and then the lecture would be vaguely related, not vaguely related, but would be related in some sense to what has been read. For the first one, we will be talking about machine learning in general and linear regressions. So from what we've read, supervised learning. Okay, I'm gonna close the chat. I'll deal with the questions later, but for the time being, I'm gonna close the chat. Supervised learning is basically when you're trying to map a dependent variable to an independent variable. So what do you think a dependent and independent variable are? Well, take it as easy as the relationship of y equals mx plus b, a linear fit. The variable y depends on a factor x, be it time, be it voltage, really depends on what relationship you're trying to establish. And through supervised learning, we have a labeled example, and we're trying to use some features that we have for that example to create that mapping. So this differs from traditional computation in the sense that in traditional computation, we input some rules. Which are the program. We give some data, we do the computation, and we get in the result. We get the results. In machine learning, this paradigm is flipped in the sense that we give them the results. That's the y. We give the inputs, which are the features, which is the x. And based on the models and optimization computations, we're able to create a mapping from the desired input to the desired output. And this is represented in the way of a model. So broadly speaking, we will be focusing on supervised learning. Supervised learning itself can be broken down into two classes, one being regression and the other one is a classification. Classification is when you're trying to classify an example into a category. So for example, Matt was talking about Twitter. There's a lot of examples where you scrape Twitter and you try to use a bag of words to be able to classify a tweet as being positive or being negative based on its content. Another example given by the book is detecting if an email is a spam or not spam. This can also be done by the content of the email itself. Another type of supervised learning is regression problems. In regression problems, we're trying to estimate a numerical value. So let's say that we have a data set of houses in California, and we're trying to predict the price of a house. And in our features, we have features such as the number of bedrooms, location, the proximity to schools, the total area of the house, how close the house is to the beach. We can have a lot of features, and we want to map it to a pricing. So that would be our features. Our features would be what we're using to make our pricing prediction. And this is a typical regression problem. So yeah, how do we choose the correct ML model to do? Wait, is the screen sharing?
Yeah, we can see it.
All right, perfect. Yeah, because the green thing wasn't around. Yeah, I was saying, how do we choose among so many models what model we should be using? Well, here there's a nifty little map provided by scikit-learn, which is one of the main libraries done for learning. and it shows like the huge spectrum of classification and regression models that exist. So for example, you follow this flow chart, and as you get acquainted with the types of problems that you solve through Kaggle competitions or through experimentation, you'll be more suited to deciding which models to use for what problems. In this specific example that we will be using for this notebook, we'll be using just a linear regression. So let's implement this linear regression. Take that age-old question of happiness and money. Does money make people happy? I mean, some people would say yes. Other people would say there's a little bit more to life than just money. But let's think that it does to a certain extent. Well, let's not think it. Let's try to see it. Here we have a table in the notebook of countries, and our feature would be the GDP per capita. So how much economic output a person in this country is making each year, versus what we're trying to map, which is a life satisfaction rating calculated by the OECD, which is it's a body of countries. If we map out the members of the OECD, we can see that there's it seems that there might be a trend here. You know, how does life satisfaction depend on GDP per capita? Well, let's see. We think we can fit it with a linear regression, but why not verify it? We can use a method called a bivariate correlation. If you want to see it further, you can explore it in this Wikipedia link. But basically, it is a statistical test that it talks about the linear correlation between X and Y. So here you see that linear correlation, which can range between 1 and -1, is not only dependent on like how narrow the lines are, but also like the general shape, because we're trying to fit a linear regression. We're not trying to fit a more complex curve like a polynomial fit. Running the simple Pearson correlation, which is the bivariate correlation we just talked about, with a number of libraries from NumPy to SciPy. Here we can see that, for example, okay, let me go a bit more into depth in this. Here we have two data sets. So here's data one, which generates a random integer it generates 1,000 random integers and then multiplies them by 20 and then adds 100. And then data two takes this value and adds something to it. So here we can see a clear dependency between data one and data two, because of the way that like data two depends on data one. If we run this Pearson correlation with the shift enter key, which is how we run ourselves in Colab, we run it anyway, doesn't matter, because I did. Yeah, it's running. You can see that the value is pretty high, 0.899. I mean, this value won't change because the seed value is the same, but if you change the seed value, you'll see that it'll be very close to 1. And if we graph this data set, we can see that indeed it resembles one of these curves here. And data one does vary to some extent. Data two does depend on data one as expressed in our formulation. So returning to the main example about happiness and money, it seems to be a linear fit based on the graph that we saw up here. So how do we go about in finding the slope and the y-intercept to fit the GDP per capita to the life satisfaction, right? We want to know what the M and the B are in the y equals mx plus b. And there's a lot of ways to do this, but one key way, which is used in a lot of machine learning algorithms, is to try to quantify the difference between our prediction and the true value. So, for example, if we had Hungary, an example of Hungary, and we give an example of 12,000 and it returns us a life satisfaction of 7. What's the difference between that 4.9 and that 7? and how can we use that information to inform our model and make the correct parameter optimizations for the slope and the intercept, such that our line fits our model, our line fits our data better. So what we do is that we create a cost function or a loss function, and this quantifies that value, the value of the difference between our predictions and the true labels. And one of the ways to do it, I think that was seen in chapter 1, is the Euclidean distance, which is basically taking the shortest path between the one point and the other. And you can do that by squaring the difference between the x and squaring the difference between the y of each value, and then taking the square root of that. So we do this in the case of our model by this formula, which represents a summation over all of the examples that we're trying to implement, and then we just take the square root at the end to we've squared we've squared all the distance, so we're trying to take the square root. Now that we have this information, what do we do with this information? We have this value that is telling us how good our model is performing or not performing. So how do we tweak our parameters based on this? Well, we need to do a bit of calculus. So we want to take this cost function and see how that cost function varies against each parameter. So we want to see how the cost function varies against the slope and how it varies against the y-intercept. And this variation can be graphed in a hyperplane. A hyperplane is just the extrapolation of a normal 2D plane into a higher dimension. So it's a 3D plane or higher. So in this hyperplane, for example, we'd be graphing the values of the cost function across many different instances of different combinations of the y-intercept and the slope. So let's say that here we chose a y-intercept of 20 and a slope of 3, but that doesn't fit our data at all, and it's very far away from our data points. We would be at a high peak, and our goal is to minimize the cost function. So our goal is to walk slowly to one of the troughs, be it the global minimum or one of the local minimum, ideally the global minimum. So what we do is we take the derivative of these parameters that we're trying to find in respect to the cost function, and then we subtract that from the current parameters that we have. So say that we go back, we have an intercept of 20, but our gradient in respect to the cost function is 5. We subtract 5 from 20, and we start descending the hyperplane into the valley, which is the optimum point of fit of our relationship. So to summarize all these ideas, first we plant a hypothesis of like what kind of relationship we can use to build a model. In this case, we chose a linear regression because it was a very easy linear fit. And I mean, in many other cases, we're going to get more complex fits where you're going to have data that looks like in these cases where you see a 0. And in these cases, you're going to need more complex models that create more complex decision boundaries. But in this toy data set, what we're working with, linear regression is good enough. So that's what we'll be using. After that, we see what parameters we have. In our case, it was the slope and the y-intercept. And we try to optimize, tune these to the point where we get a minimum cost function. And yeah, as when we get a minimum cost function, we've basically fit our model to the data, and we can use that model to infer on new data. So by inferring on new data, we're saying that basically you're providing it new X's, new, let's say, GDPs per capita, and you're getting life satisfaction scores out of it. So now to the example itself. So here we get a git clone. We're cloning the repository that from where the example was taken, so that we can get the data set of all the OECD countries. It'll take a minute. Yeah, then you can put exclamation mark ls to see what documents are inside what you cloned. And here we go with the code example. So first, we're gonna import the data sets. Here's the data path established from the GitHub repository. So we go into the data path, and we want to fetch the data sets of OECD BLI and GDP per capita, which are going to be beneficial for our predictions. If we run this, here we can see the structure of the data that we get. So here is the one of the data sets. We get location, and we get a couple of features, none of which are particularly relevant to what we're trying to do. But a lot of the process of machine learning itself is purifying the data and cleaning it before actually feeding it into the model. Some would say that 80 to 90% of the work in machine learning is to actually play around with the data, to explore it before actually training the model. So yeah, this is the data we have. Here we're defining a function to prepare the data in the way that we would like it. So we're filtering here in this command. We're filtering for the examples that only have inequality equals tot, which means that we're filtering by total inequality, which are the values that we're going to use for our we're going to use for our scores, right? To know how good life is, the total inequality. Yeah. Next, we create a pivot table, which basically means that we only keep the values or the data that we are interested in, and we're reshaping the data frame to create a pivot table. After that, we take the other data set and we're renaming the data set. So we're renaming a column within the data set. So initially, we have the GDP per capita for 2015. We want to discard the label of 2015. We just want to rename it to GDP per capita, and that's what we're doing here. And then we're setting our countries as the indices. So instead of 0, 1, 2, we're going to have our countries so that we can use our countries to address our data. And finally, we're merging the two data frames. So the data frame of life satisfaction and the data frame of GDP per capita. That's what we're doing right here. And yeah, we're merging them on the country's name, right? And that's why we made the country the index. Here we're just full country starts. We're sorting the values from from increasing order to decreasing order. And I think the OECD has around 36 countries. So what we're doing here by removing the indices is that we're keeping some data points from training in our model so that we can then test our model and see how well it's doing. Because when you're adapting a model, you never want to test the model on the same data that you're using it to train, because that'll give you a false sense of confidence of how your model is performing. If the model itself has seen the data before, then in some sense it can already it already has the information of that data. So if it's seen it before, it will be able to make a prediction on it much more easily, and maybe it won't be able to generalize to what we're trying to test at all. It will just do well on what we've trained it on. So yeah, we just keep cleaning it here. We remove the examples that through the iloc operation. We remove the examples that we're going to use for testing, and then we end up with this data frame, which is basically just composed of the countries, their GDP per capita, and the life satisfaction rating. Here we can see the full data set that we'll be using to train our model. And then here we want to, so as we mentioned before, we want to make a relationship. We want to map the life satisfaction through the GDP per capita. So we have to split these two. Here with a NumPy, we're only taking the features from the data frame for the X, and for the Y, we're only taking the labels. And then we can visualize that based on what we have. Yeah, I didn't run a bunch of cells. Sorry, let me go back and run them. Yeah, so here we can see the data of our data set. And if we want to run our bivariate correlation on the data set that we have, we can do that. And yeah, it gets a pretty high score. And then, well, we have already talked a lot about the process of learning itself, but in practice, no one is gonna implement a machine learning model from first principle, right? There's a lot of libraries. One that we're using is scikit-learn, which is like the industry standard. So here we're just initializing the object model by calling a method for linear regression within the scikit-learn library. And then we're fitting our features into our labels. So we're using what we talked about making a prediction and then checking the true label and then tuning the parameters of the intercepts and the slope to our data set. So when we run this, we get back linear regression and the model has been fit to the data. And if we want to test it, for example, we can get a new GDP. So we're taking the GDP of per capita of Cyprus. Cyprus is not an OECD country, so it's not part of the data set. But if we use our model to predict, we get a score of 5.96, and it's calculated that the real score of Cyprus would be around 6.2. And to be honest, this is a very simplistic model. Of course, GDP per capita is not the only factor that influences life satisfaction. There's a lot of factors like inequality, wealth gap. There's not one factor that will lead to life satisfaction. So maybe that's one of our considerations that we can take on if we wanted to expand on our model. And if we want to see what kind of parameters our model found, we can use this. So here we're returning two values, T0 and T1. And one is the coefficient and the other one is the intercept. And if we print them, we can see that the slope that we found is really small, while the intercept is about 4.85. So whatever the GDP per capita is will be multiplied by 0.0005, and then will be added with this number to get the life satisfaction score. And if we want to see how well our line fits the data, we can just do that by running this. And here we can see how the line is overlaid on the data points. And yeah, here just talking about that, about how this model might be an oversimplification. We can add a lot to it. We can also use the data points that we've removed before previously up here in this section of the other OECD countries that we didn't use to train our model to the actual graph and see how our model is faring. And we can see that when we add it, actually, for some countries such as Brazil, Mexico, and Chile, and for other countries at the other tail, such as Luxembourg, our model, which is the blue line, actually deviates quite a lot from what we need to get. So we know that this is a key pitfall of our model, and that maybe we need to choose a more complex model to fit our data, or maybe we need more data or more features to be able to improve our model's quality. So also, why we ask ourselves again, why did we choose linear fit? Why didn't we choose something like a quadratic fit, a cubic fit, a subquadratic fit that can have more flexibility in the way that the line itself is drawn across the data points, right? We want maybe the boundary of the line or the line itself to be a bit more curvy, or like that's what we think, right? Why just draw a straight line when you can play around with more parameters and like actually fit the data better? And if we do that, we can see from this image what would happen on a higher order polynomial. And okay, here we're touching every point in our data set, but to be honest, this isn't optimal. And why isn't this optimal? This isn't optimal because now that we fit it in this way to our training data, we're not able to generalize to a wider data set, right? So if you get a new country, say like Cyprus, the model has adjusted so much to the data we've provided it that if it appears in one of these gaps, or if it like it's if the data point is even here, like it's not generalizing well enough, so it might lead to some very erroneous behavior when we're actually using it for inference later on. And if we would like to explore this example itself a bit more, here's the GitHub link, and you're more than welcome to see it. It goes a bit more into depth than we've done here, but yeah, that's basically the gist of it. So, I mean, after all of this, you've seen how easy machine learning can be in terms of linear regression. Like, this is the most rudimentary block of machine learning, right? And don't be misguided. Linear regression itself might be a very simple, like mathematical equation, but it is used. It's the backbone of a lot more complicated algorithms like neural networks, which we will discuss later on. But if such like curve fitting existed in the past, why is ML and deep learning suddenly rising? And this can mainly be attributed to 2 points from what we know. First of all, deep learning really started to grow after in 2010 in a contest for image recognition. A deep learning image recognition algorithm from University of Toronto called AlexNet was able to overperform the traditional machine learning algorithms. And then like that's when really deep learning started to take off and people started to like really go into it. So it's like a development that's only been like around for 10 years in terms of how much hype there is. And obviously there were other types of perceptron models and neural networks dating back to the 60s or even the 70s, right? A long time ago. But the two key factors that differentiate those times from now is the amount of data that we have. So now with the amount of smartphones, IoT devices, computers, and tech giants have data sets that are bigger than ever. Everything that you do in social media, what you like, how you interact, how much time you're spending watching a video on TikTok, that's all captured, and that's used then to fit these models to better improve predictions. And also the second important thing is computational power. And you might also have been seeing this on the news with the rise of GPU usage, which was originally used in gaming, but now is really used in data centers and cloud computing. So these two factors are what really is driving machine learning and deep learning at the moment. And that's why it's a hot and trendy field. But I mean, it can be, there's a lot more than linear regression, a lot more than deep learning. And yeah, we hope that this session in some sense would open your eyes to the possibilities of deep learning. And yeah, now we'll have an informal discussion about this week's material, which if you covered it in chapter 1 and 2 and you have any questions, you're welcome to ask us. Thank you. Let me see the chat. Does anyone have any questions? The book is called the 100 Machine Learning Book. If anyone lost track, you're more than welcome to rewatch this session or ask questions to me personally in Slack. And I hope that like, people can join the discussion in the Slack. But yeah, if there's no further questions on the book itself, then I think that's a wrap for our first session. And I don't know if Matt wants to add anything about the society or yeah, or if any other of the committee members wants to say something. Yeah, I think that there was some there was some miscommunication, and we were aiming for 1 hour, but yeah, I don't know where the 2 hour session was said, to be honest. So the coding aspect will be taking on in the advanced competition, advanced workshops. I mean, we can do some kind of exercises in the beginner workshops, and we will be doing some with neural networks in terms of how to fit computational gates, but we won't really be covering Kaggle competitions in these sessions. Yeah, so next session we'll be covering basically chapters 3 and 4. So the fundamental algorithms, which will introduce us to the basics of k-nearest neighbors, support vector machines. So these are like the most generally used algorithms, which you can see here. And here are in the sklearn implementations of them. But we will be talking about the theory of them to actually understand how they work. I mean, Aditya, sorry if I didn't pronounce your name right, but I mean, preferably you would be reading the chapters before these workshops because it's like 10 pages per chapter, so it would be 20 pages in total. And then if you have any questions, we would discuss them here, and we would like kind of go on about the topic like briefly. Okay, everyone. I won't keep you like much longer here because if you don't have any questions, like I know you want to get on with your evening, but if you have any question for me or for any other of the committee members, please forward it to us in Slack, and we'll do our best to answer it if we can or to route it to the appropriate person. Thank you for coming along and tagging along. Bye. Thank you.